Hello everyone, welcome to Q-Chem webinar number 37. My name is Joonho Lee. I'm a staff scientist here at Q-Chem in Pleasanton. Today's speaker is Professor Martin Hagorn. He's a Kenneth Pitzer Distinguished Professor of Chemistry at University of California, Berkeley. He is also a scientific advisor to Q-Chem. He is recognized with many rewards, such as Medal of International Academy of Quantum Molecular Sciences, his election to American Academy of Arts and Sciences, the American Chemical Society Fellow, and the most recent Schrödinger Medal of Warthog. Today, he'll be speaking to us on Orbital Optimized MP2 in Q-Chem. Without further ado, I'd like to turn over to our speaker.
Okay, well, thank you very much, Joonho, and it's a pleasure to give this webinar number 37. I have been involved in Q-Chem since actually 1993, so it has been a long time, but I still get quite excited about seeing the progress and the rapid developments that come from groups all around the world, really. So, you know, that is one of Q-Chem's big strengths, is the fact that we have a big community of developers, maybe more than 100 active developers. And today I will tell you about development that has come out of my group. And this is about orbital optimized MP2. And you may or may not have heard of it, so I will spend a little bit of time introducing. This is our agenda for maybe the next 45 minutes or so, to leave some time for questions. I will give some general introduction about what is this orbital optimized MP2 method and why should you care about it, and then go through what it can do, you know, how it is made up. How accurate is it? How can it be made more accurate? How can it be used to look at some molecules that actually do have strong correlations, even though this is a method, as I will tell you about, without any strong correlation? So we will finish up diagnosing strong correlations and looking at some biradicals, and then finish up by just talking about when might you want to try and use this instead of density functional theory. And it is available in the current released version of Q-Chem, and you can play around with it, and I hope you find it useful. So when we do Hartree-Fock calculations, often if the molecule is closed shell, we just assume that we do restricted Hartree-Fock, which is the top row here, labeled R for restricted. And if you do restricted Hartree-Fock, then you get one determinant, and that determinant is an eigenfunction of total spin, the projection of spin onto the z-axis, and it also has complex conjugation or time reversal symmetry. In other words, the wave function can be made real without any loss of generality. And this is a good determinant in a way, because each of these symmetries are symmetries that the real wave function has. And so if we do a simplified wave function like one determinant, well, it's nice to have those symmetries too. But sometimes the energy can be lowered by breaking those symmetries. And so this slide is really telling you about the roughly the 5 classes of symmetry-broken Hartree-Fock solutions that might be useful or interesting. So sometimes you can keep the eigenfunction of total spin, the projection of spin onto the z-axis, and just break complex conjugation symmetry. This might sound funny, and it's relatively rare, but there are some molecules where this really happens, and I'll show you one later. So in that case, the energy goes down from the restricted solution, and yet you still have a good total spin and a good SZ spin. Then the symmetry breaking that is most familiar to quantum users of quantum chemistry software is spin polarization, or the use of unrestricted orbitals, where we allow the alpha orbitals to be different than the beta orbitals, and so that's the 3rd row. And unrestricted and complex unrestricted, which is a relatively rare case, they now break total spin symmetry, but keep SZ symmetry, so still the molecular orbitals block into alpha and beta, and and spin polarization is very useful for breaking chemical bonds. In fact, it's really essential, because if you try and stretch a chemical bond without spin polarization, you then get energies that are much too high with the restricted wave function, because the restricted wave function contains ionic character that needs to be suppressed when you break the chemical bond. Okay, then the last two rows of the table are about the what are called the general orbitals, and the general orbitals well, begin to break all of the remaining symmetries, so they are no longer eigenfunctions of even SZ symmetry. What that means is that general orbitals have alpha and beta components mixed in the one orbital, and so I'll show you some examples of general orbital cases later on. So this is this table illustrates from the top row perfect symmetry to the bottom row no symmetry, but the top row highest energy and the bottom row lowest energy. This is called the symmetry dilemma of quantum chemistry. Do we keep the good symmetries like the top row, or do we get the good energy like the bottom row? Well, the choice is up to the individual, but my own preference is to break all symmetries that are possible. Okay, and I should say that Q-Chem at the Hartree-Fock level has very good tools, built-in tools for testing and testing for instabilities. So when an unrestricted solution appears, it's because the restricted one has become a saddle point. And so you can test that the same way you do frequencies on optimized geometries to see if you have a minimum. You can do the orbital analog of frequencies, which is stability analysis, and see when a restricted solution wants to break and become unrestricted or general or complex restricted. So let's begin with a very simple example. This is the hydrogen molecule, and we're treating it by Hartree-Fock theory. So Hartree-Fock is not exact for a 2-electron system, so there will be errors here. The energy curve is in green for UHF, and it's also in green when UHF and RHF are identical. And you can see that at a particular point, around 1.25 angstroms, there will be a breaking between the red and the green curves. They split, and then on the right-hand side is a scale that is not energy, but is the lowest eigenvalue of the orbital Hessian. So crossing below 0 would mean that the orbital solution has become unstable and is a saddle point. So in particular, have a look at that blue curve, which is the lowest curve, and that's the lowest eigenvalue of the restricted orbital Hessian. And it goes negative for bond distances exactly beyond where the red curve and the green curve separate. And this is called the Coulson-Fischer point for bond breaking. And at the Coulson-Fischer point, and bond lengths longer than that, the restricted solution becomes unstable, and the unrestricted one goes lower in energy. In other words, the green curve for energy goes below the red curve. And then the unrestricted orbital solution, its lowest eigenvalue is shown in that light purple, and you can see that it is positive to the right of the Coulson-Fischer point, unlike the restricted one that's negative. So thus, this is how Hartree-Fock treats bond breaking. The electrons pair happily at equilibrium at around 0.7 angstroms, and the electrons have to unpair when the bond is broken. But we only have one determinant, and the only way the electrons can unpair is to symmetry break. And so the unrestricted solution symmetry breaks the alpha electron different to the beta electron, one localized on one atom, the other on the other. And that Coulson-Fischer point, the point where the restricted and the unrestricted solutions split apart, is the onset of what is sometimes called the recoupling regime, which is where the electron correlations become strong, and therefore the role of the symmetry breaking in Hartree-Fock is to actually describe a strong correlation. And so that's a good case, and I'll now show you another very, very simple molecule that that might be less familiar to you. So this is the beryllium dimer, and beryllium has 2 electrons in the 2s orbital, and it makes a weakly bound dimer with a long bond length of about 2.5 angstroms and a weak binding energy of about 2.7 kilocalories per mole. If you do restricted Hartree-Fock, the equilibrium bond distance actually is infinity, and the dissociation energy is 0, and that's all because the bond order is 0. Basically, you get the 2s orbitals you can combine in phase and out of phase, make one bonding, one anti-bonding, but there's no net bonding, and therefore there's no minimum on the curve. However, it turns out that that restricted solution is unstable, and Q-Chem can detect that instability and follow it, and you find an unrestricted Hartree-Fock solution with an S² value that instead of being 0 is 0.9. That's almost the average between a singlet 0 and a triplet 2, and an equilibrium bond distance that is actually in quite good agreement with experiment, a little too short, and a binding energy that is in quite good agreement with experiment, a little too strong. And the orbitals are interesting. So here are the alpha orbitals that you get after you unrestrict. You can see that one of them looks very much like sigma 2s, the bonding orbital, and the other looks like sigma star 2s, except that it's all polarized to the left of the molecule. And really sigma star, instead of having the node right in the middle of the bond, is now looking, a little more non-bonding, a little less anti-bonding. And then the beta orbitals are pretty much just the mirror image of this. So you can see that if you reflect through the center of the molecule, you get the beta orbitals. And this is how you get net bonding in unrestricted Hartree-Fock. And this is another example of what one might call an essential symmetry breaking. In order to describe this molecule, it is essential, if you use a one determinant wave function like Hartree-Fock, to break symmetry. And if you do break symmetry, you get observables that are in better agreement with experiment. So that's Hartree-Fock, and Q-Chem has a great set of tools for coping with Hartree-Fock and diagnosing the instabilities. And the catch about this is that sometimes Hartree-Fock breaks symmetry when there is no good need to break symmetry, no obvious need. So for example, on this next slide, I'm showing you up the top here a very stable monoradical. This is the phenylenyl radical, which is 3 fused benzene rings. It should be a good doublet. In fact, when you look at S² by Hartree-Fock, you get about 2.05, and when you look at S² at the MP2 level, because MP2 uses the Hartree-Fock orbitals, it inherits the Hartree-Fock symmetry breaking. But that molecule is stable in solution. It doesn't react. So why does Hartree-Fock break symmetry? Well, it probably breaks symmetry because it neglects all electron correlation, not just strong electron correlations, and it can lower the energy that way. If that example doesn't impress you, then take a little piece of polyacetylene. And this is a polyenyl radical containing 31 carbon atoms, and it should have an S² value of 3/4 for a doublet, and instead unrestricted Hartree-Fock gives you 5.3. If you do MP2, it's about the same. So this is big artificial symmetry breaking because polyacetylene is actually a fairly stable material. How do you get rid of it? Well, you might just run density functional theory, and we'll talk a little more about that at the end of the talk. But if you are trying to do something that's still like Hartree-Fock itself, that has no density functional theory character, then one thing you can do is optimize the orbitals with the PT2 correlation included. And those are methods, and that is the OOMP2 method, which is basically to try and do a Hartree-Fock-like calculation, but instead of just minimizing the Hartree-Fock energy, you minimize the energy with the PT2 correlation correction added on. And the PT2 correlation correction is shown at the right there, and you can see it's very, very simple. It's basically just 2 electron integrals ij double bar AB squared divided by energy denominator differences. So that delta ij AB is the difference between eigenvalues of empty orbitals A and B minus occupied orbitals I and J. And this is a method that has been known for, I guess, going on 14 years, and it builds on so-called Bruckner methods that are much older again. And if you apply those methods, they clean up the broken symmetries of Hartree-Fock. So up the top on the left is that phenylenyl radical, now at MP2 with a nearly perfect S squared of 0.76, and for the polyenyl radical at the right with an S squared of 0.79, also very good. So I was very excited about MP2 when I first worked on it, and later on discovered that there are some difficulties with it, and I'm going to now show you the difficulties with the classical MP2 method by going back to the bond breaking of H2 and doing it with MP2. The main difference relative to a couple of slides ago is that the right-hand scale, showing the lowest eigenvalue of the orbital Hessian, which diagnoses a saddle point or a minimum in wave function space, that scale now begins at 0 down the bottom. And if you follow the unrestricted lowest eigenvalue in pink and look at the point where the unrestricted and the restricted solutions separate, you see that the lowest eigenvalue of the restricted solution is still positive. So in other words, the solutions actually don't connect. So to the right of about 1.6 angstroms in bond length, there are actually two coexisting local minima. One is with restricted orbitals, just like RMP2, and the other is with unrestricted orbitals, like UMP2, but with orbital optimization. These become different minima instead of an unstable solution that splits apart. So that means, in fact, there is a little kink in the energy curve because the restricted and the unrestricted regimes don't join smoothly. So there is no Coulson-Fischer point for MP2. To put it another way, there is false symmetry restoration at long bond distances with restricted orbitals, because at long bond distances, really H2 should be bond broken. You shouldn't be pairing the electrons. And so if you look at the red curve for the energy, you can just see it beginning to turn over at the very right of the screen. In other words, instead of the energy rising monotonically as it does in Hartree-Fock, Ru MP2 begins to turn over. And in fact, if we go far enough out, it will go below U MP2. So this is not good, and we need to do something about it. We need to change the method. And so the method I'm telling you about today is then a modification of MP2 to fix this problem and to make it substantially more useful. Okay, so this is then on to part 2, which is about an MP2 method without strong correlation. Why does that restricted MP2 curve turn over exactly? The reason is it has a bad description of the strong correlations associated with exciting 2 electrons from the HOMO to the LUMO because of the simple MP2 treatment of correlation. So we need to try and get rid of that bad treatment of strong correlation. And in mathematics, this is often called regularizing an ill-conditioned system. The simplest regularization is a level shift, and these are famous in quantum chemistry and even sometimes used to converge SCFs. If you add a level shift delta to try and restore a Coulson-Fischer point, it turns out you need a very big value, about 1 atomic unit, which is about 30 volts, which is about 30 times 100 kilojoules per mole. So it's just in the megajoules per mole regime. So indeed in the tens of megajoules. So instead we have investigated and eventually come up with an alternative regularizer that can only affect the small gap terms. So small gap meaning if a virtual level EA becomes close in energy to an occupied level EI, we're going to then multiply the 2 electron integral by a damping factor 1 minus the exponential of minus kappa delta IJAB. So if delta IJAB goes to 0, then the exponential of 0 is 1, and the integral itself is damped away entirely. In Q-Chem, both orbital and nuclear gradients are implemented, and this is a non-trivial problem to do. So a very, very talented member of my group, Dr. Joonho Lee, this work was part of him getting his doctorate, actually took care of designing and implementing this kappa MP2 framework in Q-Chem so that you can now run it today. And as I just mentioned, in the limit of 0 gap, the integral is attenuated away to 0. By L'Hopital's rule of limits, the ratio of the integral squared divided by delta, both of them are tending to 0, but the ratio rigorously goes to 0. And so this is what I mean by saying that this is a method with no strong correlation. The bad treatment of strong correlation in normal MP2 is being removed in the vicinity of small gaps. And MP2 is being left untouched when the gap between occupied and empty orbitals becomes big, because that's where perturbation theory works well. And you'll notice that this is not an ab initio theory, strictly speaking. We have introduced a parameter, kappa. And kappa OOMP2 is to remind you that there is a parameter there that spans regular OOMP2 in the limit when kappa goes to infinity and normal Hartree-Fock theory when kappa goes to 0. So the question is there a finite kappa value that makes a useful kappa OOMP2 method, somewhere between Hartree-Fock, kappa equals 0, and OOMP2, kappa goes to infinity, both of which I have shown you have problems. And so this next slide is a little bit of insight into how Joonho and I chose a suitable kappa value by looking at the Coulson-Fischer point we get in breaking the CC bond in ethane. And so on the y-axis here is the eigenvalue of the orbital Hessian. And so going through the red line corresponding to 0 is the point at which the restricted solution becomes unstable. So the unregularized blue curve never goes through 0, just like for hydrogen, but 3 different regularization values, getting stronger as kappa gets smaller, because you're getting closer to Hartree-Fock, show smaller Coulson-Fischer points, that is Coulson-Fischer points at smaller bond lengths, about 2.6 to 2.5. If we then go to ethene, you see much the same thing. And because ethene involves 2 pairs of electrons being broken, we should expect that the ethene Coulson-Fischer point occurs at a shorter bond length. And indeed it does for each of the 3 regularizers, kappa 2, 1.75, and 1.5. And then thirdly, we could go to a triple bond breaking. And now we see something funny, which is that the weakest regularizer, kappa equals 2, actually has a Coulson-Fischer point at a longer bond length, about 2.4 angstroms, than the Coulson-Fischer point for the double bond breaking. Doesn't seem right. Suggests, in fact, that regularization is too weak, that you need stronger regularization, smaller kappa. And in fact, these results together suggest that really we want kappa equal 1.5 or smaller in order to have the Coulson-Fischer point shrink to shorter bond distances when we correlate more pairs of electrons. 1 pair goes to 2 pairs, goes to 3 pairs. So there's a criterion for choosing kappa. 1.5 or smaller is preferred on physical grounds to get sensible Coulson-Fischer points. You can also then take a pragmatic chemical look at how this method works on recovering thermochemical bond energy differences, tested here on the W411 set. So on the y-axis of the plot is the root mean square error across the data set. On the x value is the chosen value of kappa. So the blue curve traces the Hartree-Fock limit as kappa goes to 0 on the left, the OOMP2 limit on the right, and you can see that in fact finite kappa is better than infinite kappa on the right, and certainly much, much better than 0 kappa on the left. So consistent with the requirement from Coulson-Fischer points of less than 1.5 1.5, it looks as though 1.45 would be a specific candidate kappa value. And so basically that takes MP2 theory, which is not very good for thermochemistry, and is slightly improved by MP2 and becomes better, significantly better, by actually doing nothing but attenuating away the strongest amplitudes. In other words, we haven't rescaled anything else. All we've done is damp the biggest T amplitudes, the biggest doubles amplitudes. And so then we should go look at some transferability tests. Well, just very briefly. Basically, you see that for radical stabilization energies, the regularization actually does not help, but it does not greatly hurt. Both OOMP2 and kappa OOMP2 are significantly better, that is more than 5 times better in terms of lower RMS values than MP2 itself because of lower spin contamination. And then interactions of neutrals with radicals, some improvement. So it looks as though this transfers. And so as a practical as a practical measure, we then choose to select kappa as equal 1.45 as our default for this kappa OOMP2 method. And if those orbitals are good, then perhaps they can also be used to get even higher accuracy than anything associated with PT2. And so I want to spend a few minutes telling you about work by Luke Bertels with Joonho on revisiting MP3. MP3 is widely considered to be a dead method in quantum chemistry. In other words, usually MP3 does not greatly improve the results of MP2 itself. And in fact, when it comes to perturbation theory, I myself have been known to say you should stop at second order or quit, but perhaps we should go back and revisit, because really the cause of problems in MP2 is symmetry breaking in the orbitals, and MP3 just exaggerates that symmetry breaking. So if we now have better orbitals that, for instance, restore symmetries in systems that don't have strong correlations, then maybe these better orbitals will allow MP3 to work better. And so the next slide is a lot of data condensed into bar graphs, where the y-axis is the root mean square deviation. The x-axis is 7 data sets, and we're beginning with gray bars representing the RMS error for MP2, blue bars for CCSD, and 0 here would be couple cluster through triples. And what you basically see is that CCSD is generally a much better treatment of the pair correlations than MP2 is, even though it's not quantitatively or chemically accurate itself, but the blue bars are always smaller than the gray bars. If we then go to MP3 and even the semi-empirical MP2.5 method that still use the UHF orbitals, you see why MP3 is not a very popular method, because basically it improves slightly on MP2 in some cases, but not significantly. It doesn't bridge most of the gap to CCSD, particularly for the RSE43 case, for instance, and the hydrogen, non-hydrogen transfer barrier heights, NHTBH38, and also the hydrogen transfer barrier heights. Basically just doesn't make much difference in the energy differences chemists care about. If we look at testing kappa MP2, the theory that I've spent the last 25 minutes telling you about, you can see that it generally improves on MP2, and furthermore, kappa MP2, the yellow bars, are typically smaller than the MP3 error bars are, despite the much lower cost. In kappa MP2 is iterative 5th order scaling, MP3 6th order scaling. So this already looks encouraging, and this is partly why we then motivated to suggest kappa 1.45 as a useful method, because look at the yellow bars compared to the gray bars, and you see that on all of these data sets, there is a significant improvement over conventional MP2. And on all these data sets, there is an improvement over MP2 as well. And I haven't put Hartree-Fock on there because the error bars are enormous. Finally, MP3 in red, using kappa MP2 orbitals, you see something really pleasing, which is that the use of those orbitals greatly improves the accuracy of MP3. And then you could take one of the data sets, we took W411, and asked, should we use 100% of MP3 or not? And the green bars are the result of Luke optimizing a fraction of PT3 correlation, which is 80%, or if you prefer, MP2.8. And while this is, in a way, a short webinar, this is a moment worth dwelling on, which is remarkably MP2.8 and MP3 using the kappa MP2 orbitals are capable of outperforming CCST on at least 5 of the 7 data sets. Very interesting. Okay, so let's summarize then. So MP2 is the simplest way to add correlation to Hartree-Fock, but it has a bad treatment of strong correlations and it can't restore symmetries that are broken in Hartree-Fock. MP2, the basic method, still has the bad non-variational treatment of strong correlation, and it has artificial symmetry restoration. That is, it loses Coulson-Fischer points. So I've told you about a method in Q-Chem, new method in Q-Chem, developed by Joonho Lee and myself, that improves on both of these problems by removing the small gap correlations via this energy-dependent exponential regularizer that takes strong correlations to 0, recovers Coulson-Fischer points, restores artificial symmetry breakings, but maintains essential symmetry breakings like when you break a bond. So it seems like symmetry breaking in kappa MP2 is a signature of strong correlation. And finally, the chemical accuracy is quite good, especially at the MP3 level. Okay, so I'm now going to spend the last 10 minutes or so talking about trying to use kappa MP2 to diagnose strong correlation. In other words, it's a method that has no strong correlation in it at all, yet it can still be applied to gain some insight into whether a given molecule is showing strong correlations or not. All right, so let me repeat myself a tiny bit just to make sure this is clear. So kappa MP2, we've removed strong correlation, and what's left is mean field and weak or dynamic correlation. We've taken out artificial symmetry breaking by optimizing the orbitals with dynamic correlation. Therefore, only essential symmetry breaking should remain, and its presence would then indicate the presence of strong correlations. And that means that we can, in fact, scan the kappa parameter to explore a symmetry breaking landscape. And the landscape would take us all the way from Hartree-Fock on the left, kappa equals 0, through to MP2, kappa goes to infinity, and we can find the critical value that restores broken Hartree-Fock symmetries. And the picture is something like the following, that we scan regularization strength from left to right. At the left-hand end of the spectrum, we have artificial and essential symmetry breaking together, and in Hartree-Fock, you're not quite sure which is which. At the kappa goes to infinity end of the spectrum, there is false symmetry restoration, and you're not sure if that restored symmetry is valid or not. And so in between is hopefully only essential symmetry breaking, and so we're going to go looking at these landscapes. And for 2 purposes. 1, because it's chemically interesting, and 2, because it shows you that the kappa MP2 method is applicable to not just very small molecules. We'll look at C60, fullerene. To most chemists, fullerene seems to be a pretty stable molecule. It's a singlet, it has a large singlet triplet gap, it's chemically stable enough to be isolated, worth a Nobel Prize indeed, has the observable characteristics of a closed shell molecule. Yet, it turns out that C60 exhibits very strong Hartree-Fock symmetry breaking, with a large energy lowering to UHF, and furthermore, another large energy lowering below UHF to complex GHF. And these are not small energy lowerings. These are on the order of tens of kilocalories per mole. So altogether very chemically significant. So C60 is a CGHF case. If you think back to the first slide I showed you about the different orbital classes, this molecule belongs to the most symmetry broken orbital class at the Hartree-Fock level. And it was Professor Gustavo Scazzeria's group at Rice that first discovered the CGHF solutions, and they concluded, based on trying to interpret those solutions, that the nature of the GHF solutions is consistent with the pi electron space becoming polyradical in nature. Each p orbital remains effectively singly occupied. So in other words, C60 is a strongly correlated molecule. You should not think about the pi orbitals of C60 as some being doubly occupied and some empty. Instead, all 60 of them are effectively singly occupied and recoupled to a singlet. This would be an example of strong correlations kind of emerging as the number of pi electrons gets large. And this interpretation is absolutely consistent with the data. But there is a question, which is the data influenced by essential symmetry breaking, the neglect of the strong correlations, or is it artificial symmetry breaking, the neglect of dynamic correlations, or some mixture of the two? And really, that's the question that kappa MP2 is then well equipped to sort out. So let's take a look at symmetry breaking in C60, and this again is Joonho Lee's work, trying to probe the symmetry breaking landscape. And so on the right is a picture of C60. Missing up the top left, which I'm about to show you, is a picture of measures of symmetry breaking as a function of kappa. So we'll look for the critical value that restores the broken symmetries. So in particular, if you're interested in restricted to unrestricted symmetry breaking, you'd look at S squared. There's another measure that I don't have time to fully talk about, mu0 and epsilon0, that characterizes the unrestricted to general symmetry breaking. And there's the plot. And what you see is that there is an unrestricted solution and a general solution. If we just focus on the S squared value, there's an enormous value of S squared, the blue curve, and it comes crashing down as the regularization is turned from infinitely strong at kappa equals 0 towards just quite strong at kappa goes to 1. And by kappa equals 1, the orbitals have actually repaired. So what does this mean? Well, what it means is that strong regularization is enough. PT2 with strong regularization is enough to restore the broken symmetry. And that suggests that the Hartree-Fock symmetry breaking is not essential, but in fact is artificial, and therefore that C60 is in fact not a polyradicaloid molecule as probed by kappa MP2. Well, I won't dwell on this, but the singlet triplet gap is quite big in C60 and is adequately reproduced by kappa MP2 and even other theories as well. And there's good agreement between RMP2 and kappa MP2. Remember, RMP2 is not regularized. So in other words, the small gap contributions, the bad treatment of strong correlation is there, yet it is not affecting the singlet triplet gap. Maybe there is not much in the way of strong correlation. You can also look at NUNs, natural orbital occupation numbers, and you find, of course, in kappa MP2, they're all close to 0 and 2, consistent with closed shell character. And then you can do it again with other more sophisticated and more expensive methods in Q-Chem, CCSD and also CCVBSD. CCVBSD is maybe worth another webinar another time, because it's a method that can describe strong correlations, and yet we see none in C60. All right, so C60 appears, that CGHF solution appears to in fact be artificial symmetry breaking. What about a more reactive fullerene like C36? Let's do the same game in C36. When we do the same game, we see something very different. So the blue curve that indicates the value of S squared, we have to go all the way towards very weak regularization, that is large values of kappa, much bigger than the 1.45 that we recommend in order to get the orbitals of C36 to pair back up and become restricted. On the other hand, weak regularization is enough to get rid of the complex general character, that's the red and the green curves, that vanishes at a very strong regularizer of 1. So we conclude here that unrestricted to general symmetry breaking is artificial, but in C36, the restricted to unrestricted symmetry breaking is in fact essential, and therefore C36 seems to be a molecule that shows strong correlations. And you can then go cross-check. It's got a much smaller singlet triplet gap by quite a large factor. The results now vary strongly by methods, suggesting that sensitivity to strong correlation now matters. Our best number is the kappa OOMP2 number with spin projection, which I'll talk about in a little bit. It gives a singlet triplet gap of about 8 kilocalories per mole. And the noons begin, the natural orbital occupation numbers begin showing numbers that are significantly different than 0 and 2, not just by kappa OOMP2, but also by methods like CCVBSD that are capable of describing the strong correlations. So different levels of theory seem to agree on the fact that trying to interpret symmetry breaking in Hartree-Fock as strong correlation is tricky because there's also artificial symmetry breaking. All right, and now just a few words about trying to treat strongly correlated systems with kappa OOMP2. Well, the simplest kind of strongly correlated system are biradicaloids, biradicals and biradicaloids, and we can talk a little bit about different kinds of symmetry breaking that describe different kinds of singlet biradicals and biradicaloids. So I said at the beginning, if complex symmetry breaking occurs, then you preserve the spin symmetries and you get a single determinant of complex orbitals. A single determinant of complex orbitals is in fact a multi-configurational wave function, and this has been known for nearly 50 years or so. Singlet oxygen is the classic example, because basically you have pi x and pi star x and pi star y orbitals that are half occupied, and if you mix them via a complex restricted wave function, that is making orbitals that are pi x plus or minus I pi y, that's the single determinant of restricted orbitals. That has multi-reference character, and the multi-reference character comes in sort of two pieces: a stabilizing or pairing wave function that describes the strong correlation well, and a destabilizing open shell singlet that comes along because of the symmetry of the single complex determinant. It turns out that C30, another reactive fullerene, actually exhibits essential complex symmetry breaking. C36, however, does not. So when does a molecule have essential complex symmetry breaking and when does it not? Well, we can say it's something to do with partly occupied degenerate orbitals that are perpendicular to each other. That's the common characteristic. But in general, you've just got to check. You've got to use stability analysis and check. If the molecule doesn't exhibit fundamental, essential complex symmetry breaking, then you can still use the unrestricted solution if essential unrestriction occurs, and there's only one spin contaminant. Then the famous Yamaguchi spin projection can say, well, look, what we get when we have essential symmetry breaking is an E broken symmetry. And then we can go look at a triplet that hopefully has little or no broken symmetry, and we can figure out what is the mixing involved and do what amounts to spin projection to disentangle the true value of the energy for the S equals 0 state by the formula on the left. And on the other hand, it's risky to do that with Hartree-Fock because there's artificial symmetry breaking. It can also be risky to do it with DFT because there can be artificial symmetry restoration. But with kappa OOMP2, this is a very nice method for a biradical. So if you find S squared consistent with just one strongly correlated pair of electrons, for instance, an S squared of around 1 or so, then you can use that projection formula. And you can then do a bunch of triplet-singlet gaps. And by a triplet-singlet gap, I mean the triplet is the ground state, the singlet is the excited state, the triplet is a good single determinant, the singlet is a complex restricted or a spin projected determinant. And you can get good results either way, only after you either look for the complex restricted solution or do the approximate spin projection. You can see that improves the area of the raw kappa MP2 method by roughly a factor of 5 or 6. So that shows that a class of strongly correlated molecules can be treated nicely in this framework. And C30 I already mentioned. Standard MP2 gives erratic results, but if you apply complex restricted MP2, you get a result actually that agrees to within about 0.2 kcal per mole of the approximately spin projected one. So the last 2 rows of the table are methods that can adequately describe the strong correlation in C30 by essential symmetry breaking, followed by spin projection if you are actually spin polarizing. Okay, so let me wrap up. I've gone a little longer than I wanted, but hopefully being a bit slower might have made it a bit clearer. Anyway, don't hesitate to ask questions to try and clear things up as soon as I finish. But anyway, in kappa MP2, we've separated essential from artificial symmetry breaking, and this is not just this is useful for interpretation. It's like a diagnostic for strong correlations. And it resolves, we believe, the ambiguous origin of CGHF solutions reported previously. We suggest that in C60, the symmetry breaking is primarily artificial, namely that the C60 molecule is not, in fact, strongly correlated, and kappa MP2 restores symmetries for even quite strong regularizers. On the other hand, C36 is biradicaloid. And if you then need to get a good number for a system you've diagnosed as biradicaloid, spin projection and complex restriction are 2 suitable approaches. All right, well, there's one last elephant in the room, which is when is kappa MP2 useful in the context of a normal workflow? And a normal workflow is typically using DFT because it's computationally cheap and more than adequately accurate for many chemical problems. But DFT has 2 modes of failure, which are highlighted in red, the 2 different modes. The first is the delocalization failure, which is that DFT sometimes fails due to limitations of the exchange functional. And this quite often leads to artificial symmetry restoration. So for instance, the argon dimer cation, if you pull it apart using almost any density functional, you get 2 argon 1/2 pluses, and you get an energy that is below the energy of argon neutral and argon cation. And so that symmetrical dissociation is a failure of DFT to break symmetry and give you an argon atom on one side and an argon cation on the other side. And the same kind of thing shows up, for instance, if you take an electron out of a piece of DNA with a cheap density functional like a GGA, the hole that is produced tends to spread over the entire molecule. Or if you put, for instance, the NO radical in a box of water, you make either a big cluster or a periodic system out of it, the odd electron, instead of being on NO, spreads out so that a little bit of it is on each water molecule. So that kind of problem can be avoided by using kappa MP2 without any further correction. And then there's the strong correlation error, and that's really what we focused on quite a bit in this talk, but without thinking about DFT. DFT, of course, uses just one determinant, and it either keeps symmetry or breaks symmetry, but neither way can it properly describe strong correlation. And you can't rigorously do spin projection either. So treating singlet biradicaloids and polyradicaloids by DFT is a slightly difficult undertaking, and kappa MP2 emerges, I think, as having a useful place in a workflow by being a cheap black box method for diagnosing strong correlations. Their presence is indicated by essential symmetry breaking. Then you've got to do something about strong correlation itself to get good results. So I showed you for biradicals and biradicaloids, you can do spin projection. If there's more than biradical character, then ultimately you need strong correlation methods, and that would be a subject for another talk. So let me stop here and again thank the in particular, Joonho Lee, without his work and his energy and inspiration and brilliant coding, this would not be a tool you could use. But thanks to all that, it is a tool you can use. And I also want to thank Luke Bertels for helping to turn MP3 into a useful method again. I thank the funding agencies that supported students and me in doing this work. And of course, Q-Chem, which provides our platform, and we hope that you find this useful. You can, of course, also access Q-Chem through Spartan. All right, I will stop there. Thank you very, very much.
Thank you, Martin. It's a really interesting presentation. And we have our first question here. Feel free to submit more questions. So the first question is, can we predict kappa from first principle?
I'm sorry, can we predict what from first principles?
The kappa value from first principles.
No, this is really a semi-empirical method. So kappa in the end is a scannable parameter, and maybe it's a fair question. Is there a universal value of kappa that is appropriate for everything? We don't know. We don't truly know the answer to that because we haven't done the full universe of molecules with kappa MP2. But in our experience, the 1.45 value has proven useful. And if one has any concerns about that, the fallback is to scan kappa and to try and learn qualitative things. So we recommend kappa 1.45 for production calculations, and we recommend scanning across kappa if you want to understand the nature of symmetry breaking in detail. And so Q-Chem, by the way, if you're running kappa MP2, specifying kappa is actually up to the user. So we have not set up the code so that it is so that it has a default value, because this is still a brand new method. But if it shakes out so that this proves to be adequately transferable and we remain very happy with it, then we'll probably change that in the future, make it the default.
Thank you. Actually, I have a couple questions. So based on the formula, I would assume that there is no additional cost to for the MP2, right?
That is basically correct. The rate determining step looks identical in kappa MP2 to MP2. Relative to MP2 itself, there is the extra cost that comes from doing MP2 on each orbital iteration. So running MP2 or kappa MP2 is really like running Hartree-Fock or DFT, just with a PT2 inclusion on each iteration. And so that makes the orbital optimization procedure more expensive than maybe you're used to in MP2. But for molecules up to about 20 or 30 first row atoms, because the PT2 correction is very efficient, you don't see it as a very big cost increase relative to MP2. By the time you get to C60 or beyond, orbital optimization is noticeably more expensive than Hartree-Fock, and this is unfortunately not quite as cheap as Hartree-Fock, but still vastly cheaper than any couple cluster type method or any strong correlation type method.
Okay, so when you explore the kappa values, do you identify any cases where the normal MP2 outperform the OMP2, or some cases if you increase the kappa values, you will never restore the CF points?
Well, let's see. So as you decrease the kappa value, you will always restore the Coulson-Fischer points, because eventually you get to 0 and you've got Hartree-Fock.
Yes.
So you're guaranteed to be able to get back symmetry breaking. Are there cases where MP2 outperforms kappa MP2 for a molecular energy difference? I'm sure there are, because the treatment of correlation is not perfect in either method. It's just statistically better on average in kappa MP2. So it's a little bit the way people need to think about density functionals, which is there are some systems where the local spin density approximation outperforms a very advanced hybrid density functional, but on average it doesn't. And so I think it's the same situation.
Okay, cool. So we have another question from the attendees. Has the same technique been tried on double hybrid density functionals?
Great question, thank you very much. We are very interested in doing this for double hybrid density functionals, and that is work that we are actively engaged in. We think that the idea that you regularize a simple description of correlation by wave functions is something that probably should be done with almost all methods. But double hybrids, if for people who haven't thought about them, they contain PT2 as an add-on to the normal density functional energy. And so just like MP2, there will be some small gap contributions in systems where the band gap, the homo-LUMO gap becomes small.
We would like to thank Professor Anna Krylov for her excellent presentation.
Bad treatments of strong correlations.
This concludes our webinar. We would like to thank Professor Martin Head Gordon for his excellent presentation, as well as Kuan-Yu Liu for organizing, running, and moderating this webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.